Assalamualaikum and salam sejahtera to Dr. Rahmat. So I want to present about our group assignment ECAT by Group 7 Section 2. So this is our team member. Our first member is Tay Jing Guan. His number metric is CE24004T. Second member is Mesa Ana Nixon, CE240148. And myself is Nur Hakim Arif bin Muhammad Azali. My metric number is CE240049. So next, I would like to talk about introduction about our project. So the first one is fundamental component. So active filter are essential in modern electronic, integrating passive component, resistor, capacitor with active device like operational amplifier. Second is advantage over passive filter. So they offer significant benefits such as providing voltage gain, high input impedance, and better low frequency performance. So next is specific design parameter. So this project involved designing a fifth order bandpass filter with a total voltage gain of 130, a lower cut-off frequency of 3 kHz, and upper cut-off frequency of 300 kHz. So next is practical application. Is this design is highly relevant in industry, widely used in communication system. Our project is used to audio signal processing and biomedical instrumentation. So next is about our project importance of active filter and relation to current technology trends. So the first one is critical role in electronic. So active filter are fundamental for signal conditioning, noise suppression, and frequency control. And next important is superior performance characteristic. So unlike passive filter, they provide a signal amplification, high input impedance, and low output impedance while eliminating the need for bulky inductor. So last important of active filter is high precision filtering. So they allow for high order design with sharp roll off and precise frequency discrimination, making them ideal for advanced application requiring strict selectivity. Thank you.
To do section for part calculation, mempunyai low frequency adalah 3 kHz, high frequency adalah 300 kHz. So kita boleh kira center frequency F0 sama dengan punca kuasa low frequency adalah high frequency sama dengan F0 30 kHz. Bandwidth adalah high frequency tolak low frequency sama dengan 297 kHz. Quality factor Q sama dengan center frequency F0 bagi bandwidth. Akhirnya kita dapat 0.101. Total gate adalah 130. So kita mempunyai 6 stack gate. Kenapa 6? Sebab ada lower order high pass filter, tak lagi lower order high pass filter, tak lagi satu order high pass filter, tak lagi lower order low pass filter, tak lagi lower order low pass filter, tak lagi satu order low pass filter. So akhirnya dapat 5 order high pass filter tanpa 5 order low pass filter sama dengan 5 order band pass filter. So sama dengan 130 gate. So one stack gate adalah sama dengan adalah punca kuasa 6 130. So satu gate sama dengan 2.2507. For 80 filter design, voltage input yang first pass tu adalah 5 order high pass filter iaitu low frequency 3 kHz. So kita boleh guna frekuensi ini guna formula 1/RC sebab kita guna resistor dan kapasitor semua sama. So kita akhirnya kita dapat RC sama dengan 53.0516 micro. So kita letak kapasitor sama dengan 10 nipon farad. So akhirnya kita dapat resistor sama dengan 5.3057 kilo ohm. So for label positif setiap gate ni semua kapasitor adalah sama 10 nipon farad, resistor pun sama adalah 5.3057 kilo ohm. Betul next sambung pergi ke 5 order low pass filter iaitu high frequency 300 kHz. So kira-kira kalau kHz sama kita boleh guna formula 1.2 RC. So akhirnya kita dapat RC sama dengan 530.5165 nipon. So kita letak kapasitor sama dengan 1 nipon farad. So akhirnya kita dapat resistor sama dengan 530.5165 ohm. So kita boleh dapat for setiap gate label positif, resistor adalah sama iaitu 530.5165 ohm. Kapasitor ialah 1 nipon farad. Semua adalah sama. For gate state setiap gate ada 6 state kan. So total gate ada 130. So satu state gate sama dengan 2.2507. So kita boleh guna formula ni AB sama dengan 1 tambah RF per RG. Untuk kita boleh letak RG sama dengan 10 kilo ohm. Akhirnya kita dapat RF sama dengan 12.507 kilo ohm. So maksudnya ni 6 state gate ni bahagian label negatif feedback ini RF resistor RF ini adalah semua sama adalah 12.507 kilo ohm. For label negatif keluar ni R1, R2, R3, R4, R5, R6 semua sama adalah 10 kilo ohm. So total gain ada 130. So kita bagi 6, kita punya kuasa 6. Jadi 1 adalah 2.2507. Akhirnya kita akan dapat graf macam ni. Pasif S frekuensi label kilohertz, pasif Y adalah gate AB in dB. So yang pertama kita kena total gate adalah 130. In dB guna formula 20 long 10A. So akhirnya adalah 42.2789 dB. So kita lukis maximum adalah 42.2789 dB. Stop band, function band, half half filter, log off 100 dB per decatur. Lepas tu pass band, lepas tu transition band adalah low pass filter, log off sama dengan negatif 100 dB per decatur. Lepas tu stop band. Lepas tu kita nak tolak 3 PD. Okay, tolak 3 PD adalah sama dengan 39.2789 dB untuk cari low frequency kilohertz. Lepas tu high frequency 300 kilohertz. Lepas tu dengan ni bandwidth adalah 297 kilohertz. Lepas tu for center frequency adalah yang tenang adalah 30 kilohertz.
Salam sejahtera, my name is Mesa Anand Nixon and my ID matrix is CE240148. So I will explain the comparison between the theoretical and simulated cutoff frequency of our 5th order active band pass filter. So based on our theoretical design, the filter was calculated to have lower cutoff frequency of 3 kHz and an upper cutoff frequency of 300 kHz. These values were obtained using ideal Salenki filter equations where the operational amplifier is assumed to be ideal, meaning it has infinite gain and infinite bandwidth. From the previous simulation result, we can observe that the lower cutoff frequency matches the theoretical very well. The simulated lower cutoff occurs exactly at 3 kHz. at 3 kilohertz, and then with gain of about 43 decibels. This shows zero deviation and confirms that the high pass section of the filter is correctly designed using the selected resistor and capacitor values. So however, significant difference is observed at the upper cutoff frequency. Theoretically, the upper cutoff should be at 300 kilohertz, but in the simulation, the cutoff occurs at approximately 34.3 kilohertz. This results in a deviation of about 265.7 kilohertz, which is roughly 88.6% lower than the theoretical value. This discrepancy happens because the theoretical calculation assume an ideal operational amplifier, while the practice simulation uses a practical op-amp model with an finite gain bandwidth products. As the frequency increases, the op-amp cannot maintain the required gain, causing the signal to attenuate earlier than expected. In addition, our filter is implanted using multiple cascaded silent key stages to achieve a fifth order response. Each stage introduces its own bandwidth limitation and phase shift. When these effects are combined, the overall high frequency response is significantly reduced. So in conclusion, the theoretical design accurately predicts the lower cutoff frequency, but the simulated upper cutoff frequency is much lower due to practical op-amp limitation and cascading effects. This conversion highlights the importance of simulation of understanding the real-world filter behavior, especially for high order and high frequency active filters.
Conclusion of this project is: first, successful validation of low frequency design. It is because the simulation confirmed that the fifth order active bandpass filter function exactly as predicted at the lower spectrum. So the lower cutoff frequency appear precisely at 3 kHz, and the pass band gain reached approximately at 43 dB. So it matching the design requirement of a total voltage gain of 130. So second conclusion is significant deviation in high frequency response. So major discrepancy was discovered at the upper frequency limit, while the theoretical design calculated an upper cutoff at 300 kHz. So the simulation revealed it dropping significantly to 34.3 kHz. The third conclusion is impact of non-ideal component characteristic. So this drastic reduction in bandwidth is caused by the real-world limitation of the operational amplifier used in a Proteus. So operational amplifier gain bandwidth product cannot sustain the required gain at the high frequency. This limitation is further amplified when cascading multiple silent key stage to create a fifth order filter. So the last conclusion is the critical role of simulation. So the project highlight that ideal theoretical equations are often insufficient for high frequency design. It proved that software simulation is an essential verification step to identify component limitation like operational amplifier bandwidth before moving to physical hardware implementation.